One more very useful feature in vector math is a cross product, which can find a vector perpendicular to two vectors, as shown in this graphic. To compute the cross product, we take the length of the two input vectors u and v, and then multiply it by the sine of the angle between the two vectors, also multiplied by a normal vector perpendicular to the plane of the two input vectors. So here we have some sort of normal vector, vector n. So this is also geometric definition of cross product. There is also algebraic definition, which calculates the new vector using coordinates of vectors u and v. If both of input vectors are normalized, then of course we can drop the length of vectors u and v, and the formula is simplified to the sine of angle between the vectors multiplied by the normal vector. So unlike the dot product, the order of vectors here is important. If the order changes, the resulting vector is pointing in the opposite direction. So if we compute the cross product for u and v and we get vector n, if we reverse the order of v and u, the resulting vector is pointing in the opposite direction. So the cross product really gives us a pretty consistent orientation in 3D space. If, for example, we have the usual x and y axis in space, then the cross product is pointing in the direction of positive z-axis. So let's verify this. So let's take an example of two axis vectors, vector pointing in the direction of x and vector pointing in the direction of y. And we construct these vectors using GLM vector 3 data type. So we have these two vectors and compute cross product using GLM cross. So let's take a look, and I'm just displaying the result right away. Alright, so we run it, and clearly the resulting vector that I get here, the result of this cross product, which I label here x cross y, is the vector pointing in the direction of positive z-axis. Now we can try to reverse the order of vectors x and y. So now it's y cross x, and of course this y-axis vector got moved to the first position, and vector pointing in x-axis direction now is in the second position. So let's try this. And so we get the resulting vector pointing in negative direction of z-axis. The cross product has multiple purposes, including finding normals and constructing translation matrices. If we have two vectors laying in the plane, so one vector and another vector like this, and if we compute the cross product, say it's like this, then we can normalize the result by dividing the resulting vector by its magnitude, and so this will be us finding the normal vector, vector n, shown here. And if we had this shape formed by these two triangles, then each triangle would have to be constructed from individual vertices. So individual vertices don't know yet that they will belong to a plane like this. So therefore, it's a very common practice that we supply the normals with each vertex as part of the vertex attributes that we send to the graphics card, together with vertex coordinates and possibly vertex colors.